Okay, so hello everyone. In this video, we will cover flow control protocols. So in this video, we will discuss stop and wait protocol, go back and protocol, selective repeat protocol, and its detailed summary. So if we talk about keywords related to this topic, so first is window size. Window size is what? It determines how many data units like packets or frames a sender can transmit before waiting for an acknowledgement from the receiver. Okay. Second is sequence number, a unique identifier assigned to each data frame or byte transmitted. Okay. Third is acknowledgement, signal sent by the receiver to the sender confirming that data packets have been successfully received. Okay. The important point here is in question they can give bit size or number. From that we will calculate window size. Okay. These are the keywords related to this topic. We will discuss it in further slides. Okay, let's start with our first protocol, stop and wait protocol. What we generally do in stop and wait is quite simple. Okay, think of it like having a conversation where you wait for other person to respond before saying your next sentence. Okay, here how it works: I send one packet or one frame. Until I don't get an acknowledgement, I stay stopped. What I mean is, I send one frame, now that frame will reach the receiver, and then the receiver will send an acknowledgement. Only when that acknowledgement reaches me, then I send the next frame. Okay, this is the complete concept of stop and wait protocol. That's exactly why it's named stop and wait protocol. Okay, it means you just sit peacefully after sending the frame until you get the acknowledgement back. Okay, now what exactly is the concept of acknowledgement? An acknowledgement basically means it's something which tells you that your frame has been accepted and reached successfully, so that you can send the next frame. It's like when we do online transaction, it at the end it tells us whether the transaction was successful or not. Now if the data reaches successfully, then obviously the receiver will send an acknowledgement. If it didn't reach, then there is no point in sending an acknowledgement. The acknowledgement will only be sent when the data reaches successfully. Okay, in this slide here is some theory point. Pause the video and read it. I will explain it in diagram also. Okay, for your written notes you can pause the video and write it down. Okay, now concept of sequence number is very simple. We will calculate it with the formula of 2 power m. M is the number of bits given in the question. Okay, I have clarified it before. Let's say m equal to 1. What is the sequence number? 2 power 1. Okay, so sequence number is 2. So how many sequence number? 0 and 1, and it goes on like 0 1 0 1 0 1 0 1. Okay, for m equal to 2, sequence number is 4. So we will use 4 sequence numbers: 0 1 2 3. Okay, and it goes like 0 1 2 3 0 1 2 3 and so on. Okay, it works like that. Now in stop and wait, the sequence number we use are just 2, 0 and 1. Why only 2? Because here the sender window size is 1 and the receiver window size is also 1. Please note this, it's very important point, and there are high chances of this question appearing in the exam. Sender window size means how many frames can leave from my window at once. So only one can leave. The receiver can also accept only one at a time. We can neither send frames more than this nor accept more than this. Okay, keep this in mind. We need two sequence number here. And what two sequence number we can use? 0 and 1. Now let's check out how this work in practice. Here I send frame number 0. Always remember about acknowledgement. When the receiver accepts frame 0, it moves to expecting frame 1. This means it now wants frame 1. So it will send acknowledgement 1. We never send the acknowledgement of the same frame that we just received. Okay, always remember that acknowledgement always come for the next expected frame only. Okay, so the receiver sends acknowledgement 1, the sender then sends frame 1, and it reaches the receiver, and this way the process continues. Okay, but let's suppose the sender sends frame 1 and frame 1 get lost on the way. If frame 1 gets lost, then the receiver doesn't receive anything. If the receiver doesn't get anything, then how can it send an acknowledgement? It won't send any acknowledgement. Then what happens? The sender waits up to the timeout timer, okay, hoping to receive the acknowledgement. But when it doesn't arrive, what do? We restart, or you can say we resend that frame. Okay, now here you can see we resend frame number 1. The receiver accepts it and moves to expected frame 0. Now the receiver asks for frame 0. The sender receives this request, knows that the receiver wants frame 0, so it sends frame 0. Now sender sends frame 0, the receiver accepts it, and after accepting it, it moves to expected frame 1 because it will send the acknowledgement for frame 1. Now let's consider another scenario. What if the acknowledgement gets lost? The sender will again wait up to the timeout timer, hoping for it to reach. But if it is still not reaching, then we will again resend that same frame. When we resend that same again, let's say the receiver is asking for frame 1, but the sender sends frame 0. In this case, the receiver will discard frame 0 because it knows it wants frame 1 and might wonder why we send frame 0. From this situation, the receiver can understand that maybe the acknowledgement got lost on the way, so it will send the acknowledgement again. When the acknowledgement reaches the sender, then everything will continue working properly. These are small but important cases. Next come go back n. Go back n is called a sliding window protocol. This uses a sliding window, whereas the first protocol, stop and wait protocol, was not a sliding window protocol because it had only one window slot. In go back n, the window is bigger. Pause the video and write down these important points. I will explain it using diagram. Okay, remember, in go back n, the size of window is very specific. In go back n, size of sender window is 2 power m minus 1 and size of receiver window is 1. Always remember, sender window size is 2 power m minus 1 and receiver window size is 1. Now what is m here? M is the number of bits we use to represent the sequence number. Let's say I represent sequence number using 2 bits. So the value of m is 2. I am using 2 bits to represent the sequence number. The total number of sequence number is 2 power m. So if m equal to 2, then total sequence number is 2 power 2, means 4. The sequence number are 0, 1, 2 and 3. Here also we have 0, 1, 2, 3. It runs synchronized. After 0, 1, 2, 3, again there is 0, 1, 2, 3. This way it remains synchronized. Now look, what is the sender window size? 2 power m minus 1. That means 2 power 2 minus m equal to 4 minus 1 equal to 3. Okay, so if you look at the diagram, you can see the gray part is window size. Okay, the window cover 0, 1, 2. That's 3 frames. But always remember, the receiver window size is 1. This means the sender can send multiple frames at a time, but the receiver says it can only accept one at a time. Now, here is important point. The window size should be less than 2 power m. The window size should not be equal to 2 power m. If the window size equal to 2 power m, then there is a problem. How? Let me show you. Let's say I send frame 0, 1, 2. What was my window size at the start? 3, because 2 power m minus 1 where m equal to 2, so 2 power 2 minus 1 equal to 3. I sent frame 0, 1, 2 as per my window. Okay, now suppose all the acknowledgement get lost. Okay, this one is lost, this one is lost, this one also lost. What will happen? As the receiver accept frame 0, it moves to expecting frame 1. When frame 1 reaches, it accept frame 1 and moves to expecting frame 2. When frame 2 reaches, it accept it and moves to expected frame 3. Now the receiver's pointer reaches 3. It wants frame 3 and keeps sending acknowledgement for frame 3. But that acknowledgement is lost. The sender waits until timeout, and when timeout occurs with no acknowledgement received, it thinks the frames were lost. So it will again send frame 0, 1, 2. When it sends frame 0 again, what is the receiver expecting? Frame 3. When frame 0 arrives but the receiver expects frame 3, what will the receiver do? It will simply discard that frame 0. Okay, and it should discard it because it has already accepted frame 0 before. If it accepts the same frame again, then there is a problem. But look at this scenario. Here I took the window size equal to 2 power m. I took the window is include frame 0, 1, 2 and 3. That's 4 frames, okay, which equal 2 power 2. But let me explain why this creates a problem. We send 0, 1, 2, 3 together. The receiver accept frame 0 and move to expecting frame 1. Then expect frame 1 and move to expecting frame 2. Then accepted frame 2 and move to expecting frame 3. And after expecting frame 3, look where the pointer is standing at frame 0. The receiver now wants frame 0. The sender waits, timeouts occur and no acknowledgement for frame 0, 1, 2 and 3 and reach back. The sender thinks, okay, no problem, I will send frame 0 again. Why? Because there is no acknowledgement received, so it will resend the frame. When the receiver sees that it wants frame 0 and frame 0 has arrived, it will accept it. This is the problem. This is not the new frame 0 arrived. This was the old frame 0 that was already processed. The receiver will accept the same data again, which is incorrect. That's why the window size should always be less than 2 power m. So how much should we take? 2 power m minus 1. Why reduce it further? Well, 2 power m minus 1 is the optimal answer that avoids this problem. Okay, now remember these important points about go back n. Out of order packets. Can the receiver accept out of order packets? Before that, what is cumulative acknowledgements? Let me explain with an example. Here in the diagram, the sender window covers frame 0 to 6. Since m equal to 3, so 2 power 3 minus 1 equal to 7 is the window size. The value of m is 3, meaning we use 3 bits to represent sequence number. So the range becomes 0 to 7. So the window size is 2 power 3 minus 1 equal to 7. So the window covers frame 0 to 7. The sender sends frame 0, 1, 2, 3, 4, 5, 6. all frames in the window. Let's suppose frame 0 gets accepted and the receiver moves to expecting frame 1. Frame 1 gets accepted and the receiver moves to the expecting frame 2. Frame 2 reaches the receiver and should send an acknowledgement 3. But let's say acknowledgement 2 gets stuck on the way. Okay, it lost. Now the next frame, frame 3 arrives and the receiver accepts it. Since it's the next expected frame, the receiver sends acknowledgement 4. When acknowledgement 4 reaches the sender, what will sender understand? The sender will realize that frame 2 was also accepted. Why? When acknowledgement 4 arrives, it means the receiver is asking for frame 4. The sender realized that its previous acknowledgement might have been lost. Okay, but since we use commutative acknowledgement here, acknowledgement 4 tells the sender that frame 0, 1, 2, 3 have all been accepted. Okay, commutative acknowledgement means that instead of sending separate acknowledgement for each frame, you can send them combined. When acknowledgement 4 comes, the sender knows that 0, 1, 2 and 3 are accepted. Similarly, when acknowledgement 5 comes, the sender knows 0, 1, 2, 3 and 4 are all accepted. Now here is key issue with out of order packets. Let's say I send frame 0, 1, 2, 3 and the receiver accepted frame 0 and sent acknowledgement 1, but frame 1 was lost on the way. However, frame 2 and 3 reached the receiver. Will receiver accept frame 2 or 3? No. Why not? Because the receiver window size is 1. The receiver accepted frame 0 and is now waiting for the expected frame 1. Frame 1 was lost, but frame 2 and 3 arrived first. The receiver will not even acknowledge frame 2 and 3. Why? Because it's waiting for frame 1. This is the problem with go back N that doesn't exist in our next protocol, selective repeat protocol. In selective repeat, out of order packets can be accepted, but here the receiver window is not moving. It's stuck at expecting frame 1. The receiver will forcibly discard frame 2 and 3 even though they reached correctly because it only wants frame 1. So the sender will have to send frame 1 again after timeout. Okay, then the receiver window will move to the expected frame 2. Obviously frame 2 needs to be sent again and frame 3 also needs to be sent again. This problem especially arises in go back N. Out of order packets are not accepted. It's only accept packets in sequence. Okay, this is go back N protocol. Now next comes selective repeat. Selective repeat is another category of sliding window protocol. In selective repeat, remember that sender window size is 2 power m minus 1 and receiver window size is also 2 power m minus 1. So both the sender and receiver have the same window size. Notice the difference. In go back N, the formula was 2 power m minus 1, minus 1 below, but here it is 2 power m minus 1. Minus 1 is above in the exponent. Okay, let's see an example. If m equal to 2, then how many sequence number do we have? 2 power 2 equal to 4. So the range is 0 to 3. We write sequence number as 0, 1, 2, 3, then repeat 0, 1, 2, 3 and so on. Okay, the sender window size covers 0 and 1, meaning it can send 2 frames at once. Okay, the receiver window is also 2, meaning it can accept frame 0 and 1. What will the sender send at a time? It will send frame 0 and 1. What will the receiver accept? It will accept frame 0 and 1. Remember that in selective repeat, the window size should be equal to 2 power m minus 1 and it should not be greater than that. If it is greater than 2 power m minus 1, then we will have the same problem we saw in go back N. Okay, if the frame get lost, let's say the sender sends frame 0 and 1, the receiver accept both 0 and 1, but the acknowledgement are lost. The sender will send frame 0 again, but where is the receiver now? Window has moved to frame 2 and 3. The receiver says I want frame 2 and 3. Why are you sending frame 0? From this, the receiver can understand that the acknowledgement was lost, so it will resend the acknowledgement. Okay, but what if we made the window size greater than 2 power m minus 1? Let's say instead of window size 2, we take window size 3. So we send 3 frames at once, 0, 1, 2. The receiver accept all 3 frames, 0, 1, 2. Now where does the receiver window move? It moves to expecting frames 3, 0, 1. What does the receiver want now? It wants frame 3, 0, 1 because frame 0, 1, 2 have been accepted, but the acknowledgement were lost on the way. The sender will send 0 again. When frame 0 arrive, will it be accepted? Yes, because the receiver wants frame 0. It's in the receiver's current window and frame 1 will also be accepted, but this is wrong. These are the same frames 0 and 1 that were accepted previously. Okay, so duplicate frames will be accepted again. That's why the window size should not be greater than 2 power m minus 1. It should be exactly equal to 2 power m minus 1. Now let's talk about out of order packets. They will be accepted in selective repeat. Look, when frame 0, 1, 2 are sent, it doesn't mean that only frame 0 is wanted first, then frame 1, then frame 2. No, what's in the receiver window, frame 0, 1, 2 are all in the window. The receiver has opened its window for frame 0, 1, 2. Okay, any of these can arrive. If frame 0 is little late and frame 1 reaches first, the receiver won't reject it. It will say come in. But what happened in go back n? In go back n, the receiver window accepted only one frame at a time. Okay, but here the window size is 0, 1, 2. The receiver window is bigger, so it expects that any of frame 0, 1, 2 can arrive and it will accept them. So selective repeat accept out of order packets. One more important point here is negative acknowledgement. Let me explain the concept of negative acknowledgement with an example. Let's say we have m equal to 3, so 2 power 3 equal to 8, total sequence number 0 to 7. The window size is 2 power 3 minus 1 equal to 4. So the sender window covers frames 0, 1, 2 and 3, and the receiver window also covers 0, 1, 2 and 3. Both have the same window size. Frame 0 is sent and accepted, so the sender window moves to frame 1, 2, 3 and 4. The receiver sends acknowledgement 1, meaning frame 0 is accepted. Now send frame 1, 2, 3 and 4. The sender sends frame 1, but it gets lost. However, the sender also sends frame 2 and 3. Since they are in the window and both frames 2 and 3 reaches the receiver and are accepted, here's the important point. Frame 2 and 3 are accepted because the receiver window size is large. In go back n, the receiver window size was 1. So if frame 1 didn't come first, frame 2 and 3 wouldn't be accepted. But here the receiver window size is big, so it allows these frame. It says okay, come in, but the receiver is still expecting frame 1. It doesn't mean that the receiver will forget about frame 1 just because frame 2 and 3 arrived. Frame 0, 2 and 3 have arrived, and frame 4 will also arrive later, but the receiver still wants frame 1. Why? Because the complete data packet will only be sent to the upper layer when it is 100% complete. It is not like when a file is 90% downloaded, we send it to someone in the system. No, when a file downloads, it has to be 100% complete before it can be opened. Otherwise, it won't open. Similar logic applies here. So what will the receiver do about the missing frame? It will send a negative acknowledgement for the frame 1. It means frames 2 and 3 have reached me, but frame 1 didn't come. The negative acknowledgement contains the sequence number 1. Okay, so what does this mean for the sender? If the receiver didn't send negative acknowledgement 1, what acknowledgement might it have sent instead? Let's say it sent acknowledgement 4. If it sent acknowledgement 4, what would happen? The sender would understand that frame 0, 1, 2, 3 are all accepted and it needs to send frame 4. The sender would send frame 4 and the missing frame 1 would be left behind. Okay, so that's why the receiver send a negative acknowledgement. From this, the sender knows that the frame hasn't arrived. This way the process continues. Okay, now you can see a table on the screen. It contains all the features I have explained earlier in the video. But what is the formula of efficiency in all these protocols? In stop and wait, efficiency equal to 1 upon 1 plus 2x. Now what is x here? Propagation time upon transmission time. These times I have explained in our previous videos. Okay, now what is the formula of efficiency in go back n? Efficiency equal to n bracket 1 upon 1 plus 2x. What is n here? Sender's window size. What is sender's window size in go back n? 2 power m minus 1, and this formula is same in selective repeat also. This is efficiency in all these protocols. So that's it for this video. We will meet in next video. Until then, bye bye.